When you're doing SPC, the answers you're getting are not always correct. Sometimes you get a signal, so you get a warning, but nothing's really happening, and very often you do not get a warning when actually your process has shifted already. Let's see why. Hello, I'm Tom. Welcome to my channel, where we talk about continuous improvement in an industrial setting. In today's video, it's about SPC, statistical process control, and then specifically about those rules that we use to indicate whether we have something happening to our system, so a deviation, a shift of our process, or that things are still completely normal as we want. And this is a bit the thing, right, with SPC. We'll go over the basics again, but the big thing to start off with is that the goal of SPC is to understand and incorporate this knowledge that a process has random variation. There will be some parts that you make, some product that you make that simply is a bit different, although the center line of your process has not shifted yet. So if you're making stuff from time to time, a big part or a very small part will drop out of the system. Now, if you measure that part and then correct down if you have a big part or up if you have a high part, then you are correcting the whole system while actually the system itself hasn't changed. You just got this, stupid big or stupid small part. And more often, when you have a little shift and you get, these little bit bigger, little bit smaller parts, that is something you really don't want to react to, especially not by moving the system, because you will be introducing more variation. Now, that's the goal of SPC. And let's also quickly go over what are those basic rules, and then we'll get into the meat of this video, which is how much chance do you have that you're actually getting a wrong signal, that you're interpreting the wrong stuff, and what is this whole thing with the sigma shifts of your process? How does it influence it? But as I said, first the basics, and that is we have this control chart. So you have your mean value that you should have the process at, and we cannot see what the process itself per se is doing. We see what a number of products that come out of this process are doing. So we have this sampling, but we know from previous data that this is the mean of our process. That's what we want. And then we have this plus and minus 1, plus and minus 2, and plus and minus 3 standard deviations from the mean. So what we then always say is there will be a lot of data points between this plus and minus 1 standard deviation from the mean. So it will be centered around the mean. You get a good 68% here between those. And the further you get away from the mean, the lower the chance that a point will be there just by coincidence. But even outside of 3 standard deviations from the mean, sometimes you will get just one sort of random part having that weight, that measure, and still it doesn't mean that your process has shifted. Now, what then this whole SPC does is there are a couple of rules that all look at what are, and all of these dots, by the way, they are all samples that we took, and we are measuring them and plotting them on our chart, and this is a run chart that just flows around and flows further with time. And at some point here we say, oh, this is, something went under 1 standard deviation, but if it's only 1, then we don't really care, because we know that from time to time this will happen. And then here something happens. We've got a couple of them that are a bit too high, and then 1, 2, 3, 4 out of 5 are over 1 standard deviation. And then we say that is a bit strange, because in a completely random, normally distributed process, we would not expect 4 out of 5 to hit over 1 standard deviation. We would also not even expect 1 to go over or under, in this case, 3 standard deviations. So there are these rules to pick up. Is this process still centered? Process, and I just drew a couple things here. This is not nicely normally distributed, but the idea is that this, up until here, the process is still basically centered. So can this happen? Yes, sometimes it can happen, but usually this indicates that the process has shifted a bit. Now, what do we actually want to know? And this is something that you do not see in a lot of videos and textbooks, and that is that when the process shifts, you basically, you get the same, a bit higher, a bit lower. Here, what you see is at some point the process has shifted, and we get this new center line with a couple above, a couple below, and suddenly you see a lot of higher than 1 standard deviation, higher than 2, even higher than 3 standard deviations. Now, this area here, we will quickly pick up on it. This will trigger, that will trigger, this will trigger. Those are all specific rules. Here, the 4 out of 5 above rule will trigger. So that is the idea. You have a lot more chance to trigger one of the rules when your process has shifted. Now, in this case, I shifted it by 2 standard deviations, which is quite a bit. But in general, the higher you go, the higher the chance will be that you trigger one of the rules. When we trigger one of the rules, we at that moment have quite a serious expectation that our process may have shifted. We're not fully sure yet, but it is a very strong signal. And maybe more importantly, as long as the rules have not triggered, we will not touch the process. And this is also the main thing how to use it. As long as you don't get a signal, don't touch the process. That is the safe way to go. The other thing is, when it does move, don't always just move the process. For instance, when you get this, we've got 4 out of 5 over 1 standard deviation on top, then that should trigger looking into what we are doing, looking into, do we have a high or low problem? Should we now correct our process? But that you do only if you find something, right? Don't automatically correct it, because then you may get into something like this. Hey, we have a low point, we automatically correct the whole system up a bit, and now the system has changed. So what you're looking for is checking. So when you get a signal, checking what goes wrong. And the reason for that is that there's actually a chance, and it's not a super high chance, but when you do enough tests, it will become almost certain that you will hit it from time to time. There's a fair chance that you are getting that signal without the process having shifted. Now, for that to understand, and that is basically what this video is about, we have to, and let's check just the top side now. This whole thing works also the other way around, and we're also going to look for now only at those above a certain level rules. So those are the above 3 sigma, 2 out of 3 above 2 sigma, 4 out of 5 above 1 sigma, or 9 above the mean. All those things can also be the same for below, right? So outside of 3, outside of 2. And to understand what's happening, let's first see what the chance is of getting one of your points in a normal situation, so a normally distributed process that has not shifted at all, higher than the mean. Well, that chance is 50%, because basically you are equally likely to hit it above or below the mean. Now, hitting it above 1 standard deviation, that's only 16%. Above 2 standard deviations is 2.3%. Above 3 standard deviations is 0.13%. So basically, when you get one hit outside of your 3 standard deviations, there is actually a 99.8% chance that it really has been shifting. There's also a 0.13% chance that your process was actually fine. You got a trigger, you are going to check it out, but the best thing you could do is do nothing about it in the end. Now, how does that work, and why don't we pick 1 or 2 standard deviations? This has to do with the economy of checking, right? So you don't want your operators or your control technicians to go in and check your setting the whole time, and you definitely don't want to automatically correct. See, we are checking these things many times per day. By the way, this is also one of the reasons why I would not advise checking every single product if you've got 100 a minute coming out, right? Because if you've got 100 a minute coming out with this percentage, then within the hour you will have a hit every time. So your operators will start to trust, well, more their instinct than the system. They will change the rules. And it is good in this case, because if you are measuring so often, the logical thing to do is to make subgroups and keep the same rules. But the thing that otherwise you have to do is you have to change these limits. You really have to look at it as an economics of, I don't want a process shift to go undetected, but I also don't want to send my operator into the field to check this machine again totally, and maybe to change the settings. Well, he shouldn't have done that. So that's the choice you are putting in your control system. That is what lies behind the choice of, okay, why 3 standard deviations? Some people have suggested that 3.5 standard deviations would be better if you take subgroups of 100 instead of 25. There is a lot of statistics in the choice how you put your control system into place. Now, taking the basic stuff, right? So we're building it up with the basic stuff. This rule gives you 0.13% chance of wrongly stating that there is a very likely process shift. So that's the one thing more than 3 standard deviations. Now, 2 out of 3 points higher than 2 standard deviations. You see, 1 point higher than 2 standard deviations, that gives us 2.3% chance. But that's why we extend it a bit. Well, in the economics we just talked about, 2.3%, that's once every 40, okay, a little bit more, but once every 40 measurements. So if you're measuring every minute, you got it within the hour. If you're measuring every 10 minutes, okay, maybe it would be acceptable, but see, that is where it goes wrong. So you want to have this go down. And how to do it is to say, I'm not going to trust a single hit above 2 standard deviations. I would like 2 hits. Now, if you want 2 hits per se, then you're going to miss a couple. So in the end, the rule was made, and these are just guidelines. So use them when you're starting out and don't just go ahead and change them, right? These are pretty well-defined rules that work, but in the end, they came to 2 out of 3. So if you have too high, okay, too high, then it still hits, it still gives an alarm. And of course, if you got 2 just behind each other, it will also give you an alarm. The chances of getting that when you have a normal, centered, normally working process, they are still 0.11%. Now, those things also continue for the other rules. So 4 out of 5 higher than 1 standard deviation, you've got a 22.22% chance of getting a wrong error message. So everything was fine, but we still get an alarm. And even for 9 points, all of them higher than the mean, there is a 0.20% chance that this just happens to a completely random system that is normally centered. Now, these are very low percentages. On the other hand, they don't stack also, by the way, so that makes it good. Implementing all 4 rules does not mean that you suddenly have 66.66% chance, but it will be somewhere around 0.3 or so % chance that you trigger one of the rules while you should not be triggering a rule. Now, these are the percentages that, well, you get a wrong warning when you should be getting a warning. Let's look at the different side of this, and that is our process has shifted, in this case even by 2 standard deviations. I would hope that we find that this gets noticed in our statistical process charts, but spoiler here, they will not be 100% yet. So what are the chances that this rule here, we'll get 1 over 3 standard deviations, hits when we know that the process is actually here? We still use the original limits, of course, right? So we assume that this is your process mean, and that these are plus and minus 3 standard deviations of what we know our process should be doing. In the meantime, our actual process has changed, it has moved up, and now the mean of our changed process is at the level where the original process would have 2 extra standard deviations. So basically the whole same normal distribution will be around this point. What this does is it changes the chances of falling within these areas. So logically, falling over 2 standard deviations is now 50%. Right? I mean, this is basically the new mean of our distribution. But the funny thing here is this one, it takes more than your 50%, and especially that one takes a lot more. So falling within, and now we have to think about how the new distribution basically is. This is minus 2 standard deviations, and anything that is over, that actually has a very big chance of hitting. Because if you remember, going over 2 standard deviations is only a bit more than 2%. So getting anything up until the lower border, the lower limit of those 2 standard deviations, is going to make it 98% sure that we hit it here. Now, what does this do to our rules? The first one, simple one, is the hitting over 3 standard deviations. That becomes 16% chance, the same as we had here with 1 standard deviation higher than the mean, and we only need 1 of them. But the other rules, they have their special way of calculating 2 out of 3, 4 out of 5, and they get a lot better at detecting this shift, although it will also take a bit longer. So when you use this 9 points have to be above the mean, basically these percentages, they sort of just stay the same almost. If you have 9 consecutive points with such a high percentage, even though you have to multiply it every time, you still get over a 98% chance that you will trigger this rule when your process has really shifted 2 standard deviations. For the rule that says I want 4 out of 5 over 1 standard deviation, it goes down to 84%. The 2 points over 2 standard deviations, actually it only has a 50% chance of triggering this rule. And that means that even with such a big process shift, there is quite a serious chance that we will not find it. And that is also one of the reasons we put these longer rules in place. You see, the checking 5 of them or checking 9 of them, those rules, they are a lot better at detecting a change in the process, because they are good in measuring smaller changes, but they do it over a longer period of time. And why a longer period of time? If you would check 3 out of 3 over the mean, then the chance of getting it wrong when actually the process has not moved becomes too high. So there's these trade-offs are in there. And this is one of the reasons why we use multiple rules. The only going over 3 standard deviations rule, that one is actually in many control charts, let's say the basic control charts, they will say that this is the only rule you really need. So they will say just look for a signal that goes over 3 standard deviations and you will be fine. Now that does have a nice low percentage of errors, but actually if I'm only 16% sure that I will get one of these, that means that still in 84% of the cases I will not get a hit on that. So is it a good way? I don't know. Now hopefully, and this is it depends on how well you are in statistics already, but hopefully you will have spotted one sort of problem in this. So there is a 16% chance that I will check it, I will see it with only 1 point. So immediately after we have this process shift, there is a 16% chance that I will get it. This one takes 3 or even 5 points to measure before I even get an answer, right? So this one here, I have to wait longer. So what we can also do is we can say, well, since apparently if you want to introduce more rules, right? If we want to introduce this third rule here, apparently you're okay with having to wait a bit longer. But if you check it 5 times, well, then this system, the chance of scoring over 3 standard deviations will also have increased because you have 5 opportunities to hit it. It is not exactly 5 times 16. Probability doesn't work like that, but it gets pretty close. So let's check. If we check our system 5 times, so, and I see now, my apologies, I switched the colors around, but if we are at our original level, then triggering an over 3 standard deviations was 0.13, right? If we check it that 5 times, so what is the chance that we accidentally trigger a over 3 standard deviations in 5 measuring points? Then we are already up to almost 0.7, 0.67. That also indicates that this rule also has its problems, right? When you extend it, you get to pretty high numbers already. But the nice thing is that it's not just 16% chance that you trigger if you take 5 measuring points and the process has changed. Actually, if the process really has changed, the chance that you will get at least one hit over 3 standard deviations is almost 60%. It's 58%. And the funny thing is, if you check the same with the other rules, then you will see that if you take 5 measuring points, so there is a number of combinations that you can get 2 out of 3 in a series within these 5 points, and if you add them all up, so one time that would be 0.11, but if you check all those options that you get in 5 points, you get up to 0.25% chance that you trigger it wrongly. The good thing is you do also get this, well, 56 in this case, % chance of triggering it correctly. So that is the nice part about it. And well, this one we basically already saw. Why is the 0.28 a bit higher? Well, that is because for this I did say I don't really care about the 1, 2, 3, 4 times a hit and then not, because you would have triggered it already one before. So technically this should also have been probably changed to 0.22, but I used one type of calculation on this, and that is just all the possibilities of getting 5 points that would trigger one of these alarms. So we keep these stats, right? So if your process has changed, has shifted by 2 standard deviations, you got your 84% chance of finding it. And this really is the reason why you use multiple systems. Oh, and by the way, why do I not have that rule in? Well, in 5 points, I cannot test 9 above the mean. So I will need more time. And this is why these rules are in. The rules that are measuring closer to the norm, closer to the mean, but they use more measuring points, those rules, they are better in predicting that there really was a shift. They are also, and it does depend a little bit on how you measure for their small, for basically the sample sizes, the point sizes, based on their own rule. They may have bigger chances of giving you a wrong signal, but if you compare it to the rest of, taking 5 points for all of them, then you see that actually they are better in almost every way, except, of course, that they are slower. So that is one of the things you want to notice your process shift as soon as you can. So you want to get a signal to go check your process and maybe correct it as soon as possible. And that means that there is value in keeping this over 3 standard deviations and keeping this 2 out of 3 standard deviations. 2 out of 3 points over 2 standard deviations. They will be a little bit faster. That rule could potentially already detect it after only a single one measurement after the change in your system. The other rule can detect it after 2 to 3 samples after a change in your process, and that makes them very good systems to use, that makes them a bit quicker. So a lot of numbers, a lot of percentages, information. The main thing to draw from this is that there is always a chance, and in fact there are these, there is always a chance that your SPC chart will wrongly tell you that your process is shifting. So do not change your process only based on an SPC chart. That you get this signal means you have to check your process and really get someone looking into it. The other thing is, even a relatively big shift will not be detected 100% of cases, at least not very quickly. So if you increase this to 6 or 7 points, you will really get close to the 100%. But that is also, your process can shift a bit without you noticing it. Now, within the Six Sigma community, there is this sort of magical number, the 1.5 sigma shift, or the 1.5 Z shift, that states that you cannot detect, based on SPC rules, a shift that is less than 1.5 sigma. You can, it just takes you longer. So that's a bit the thing, right? So I know I'm not going to end that discussion. There is, where is this level 1 or 1.5 or 2? Basically, there is no one value that will really give you a 100% chance that everything works out, because you have these shifting patterns. So the further your process shifts, the quicker SPC will detect it. But even if the shift is not very big, SPC will detect it if you just give it more points to look at. And the last thing to know is, don't take a huge amount of samples that you all treat as individual values in your SPC chart, because if you take very frequent analyses, very frequent samples, then even these percentages will trigger more than you would like your operator to investigate. So what you should be aiming at is that you're getting triggers, well, maybe once a day, maybe once every couple of days, things like that, right? That is a good trigger level. You should, I think, also not go for a trigger level that gives your operator some rest and says, well, let's have on average a trigger once every 3 months. Because if you take that level, then not detecting it also becomes a problem. So what would be a good basic setup to use? Well, 4 standard Western Electric rules, and make your sampling so that it is, well, at least 5 minutes apart, but also not more than 20 minutes or so, half an hour. This will give a false trigger every 1 or 2 days to every week or so, but it will also give you a relatively quick reaction to process shifts. If you take only every half hour, it means that you get easily 3, 4, so that is 1.5 to 2 hours of sampling before you notice that your process is going wrong. That can cost you a lot. The flip side is, if you go under 5 minutes, you will have your operators running to check out the line and give them false information, false alarms, more than once a day, maybe even every shift, and they will stop trusting the SPC system. So that's what I have for you today. If you like this deep dive into the percentages behind the Six Sigma SPC charts, what it really means for you, how much chance you have to get the correct answer, the wrong answer, to open it up a little bit. I know it is a lot of statistics and probability. You do not really need to know this, at least not to use SPC, but to implement it throughout your whole organization. I would really recommend that you take these things into consideration, especially if you're going to use it in multiple processes, and especially also when choosing sample sizes, intervals, things like that, and how do you train your operators to react. Now, if you liked it, don't forget to hit that like button, subscribe to my channel if you haven't done so already. And for now, I wish you the best of luck setting up statistical process control in your factory And as always, enjoy the Six Sigma journey.